let's kind of get going. So the name of the game today is going to be Notes on Exponential Functions, okay? So the general formula for exponential functions is going to be y equals ab to the power x. That's kind of the general formula. This a is going to kind of work a lot like how a... so do you remember how it was like 4 square root of x? What did that 4 do? Was it what? Yeah, it was like a vertical stretch. That's a lot what this a is going to do. Okay? That's essentially what's happening. Okay? But the really interesting thing, or the thing we like to look at a lot, is the b. That's going to be our big thing that we look for. So when b is greater than 0, we like to say that that was exponential growth. That's going to look like this. That's what it's going to look like. When b is less than 1, but greater than 0, we're going to say that's exponential decay. That's going to look a lot like this. Okay? Do we see the difference between these two? Yep. Okay. So domain, we've kind of got experience with that from our activity before this, right? The domain, or all possible x values of the function, of an exponential function, is, what is it? Can we say it louder so everyone can hear?
All real numbers.
All real numbers, right. All real numbers. The range, or all possible y values of the function, of an exponential function, depends on where the, this is a new word for the day, asymptote. It's a funny word, I know. Asymptote is. And asymptote,
How do you spell that? I can't.
okay. This is like one of the words I struggle with spelling to begin with. A-S-M-Y-T-O-T-E. I might have myself misspelled it. I'm awful at
There's a
spelling.
P, yeah.
What?
Asymptote.
Oh, I knew there was a P in it. How do you spell it?
A-S-Y-M-P.
Okay, time out. A-S-Y. A-S-Y.
M.
M.
P.
P.
T-O-T-E.
T-O-T-E. Okay. All right. Lesson of the day, Mr. B can't spell worth a poop. A-S-Y-M-P-T-O-T-E. Okay. All right. It's a line on the graph that approaches but never crosses. Ever. Never crosses it. It gets super close. So doggone close that it looks like it touches it, but never does. In math, a lot of times what we do when we graph it, so here's our function. So here's this. This is kind of what an exponential function is. A lot of times what we do in math is we'll give it like a dashed line. That's what we'll give it a lot of times in math. It's going to get so close to this line, like so close, but it's never going to touch it. Do you guys know Lord of the Rings at all? Anyone? Sort of, kind of? There's like an iconic line from it. It's Gandalf. He's like, "Thou shalt not pass." Think of that. It's never going to pass it, okay? It's an easy way to think about it. You won't pass the line. Like, the line won't pass it in exponential functions. Sometimes you do get in a situation where it'll cross this asymptote, but in exponential functions, never. Okay? Never crosses. The range will generally be, what was the range generally on our assignment? Yeah, y greater than 0. Because the asymptote will be at, where do you think the asymptote is? Y equals 0, right. Unless there is a constant that's added at the end of the function. In this case, the asymptote will follow the constant at the end. So do you guys remember that last example where it was like, I think it was like 1/4 x plus 1? I think it was something like that. This one, the asymptote actually moves up 1. and it would be at y equals 1. That's where it'd be at. Okay? If this was negative 1, where would the asymptote be at? Yeah, y equals negative 1. That's where it would be at. Okay? Any questions from that? Okay. If not, we're going to move on to exponential growth and exponential decay. So generally speaking, we get this exponential, like this is the formula for exponential growth, and this is the formula for exponential decay. That's generally speaking what it is. R is typically referred to as a rate. R is a rate. A rate equals R, same thing. And it's normally written as percent increase or decrease. This percent increase or decrease is known as our growth or decay factor. Another word you learned today. That's 2 words you learned today. Okay? Asymptote and growth and decay factor. 2 words. Good vocab lesson today. Okay? So generally speaking, these are going to be things, exponential growth is generally going to be greater than 1. Exponential decay is generally going to be less than 1. Okay? The goal is, when you do examples of these, I always think about, okay, how do I get to 1? Because we kind of want to rewrite them to make it so we can easily identify the growth or decay factor. That's what we're trying to identify. Okay? So moving on to our examples, y equals 1.5x, we're asked to state whether the function is exponential growth or decay, and then state the growth or decay factor. So is this exponential growth or decay? Growth. Why? Greater than what? 1, right. So this is growth, because 1.5 is greater than 1. Okay. Now I can kind of rewrite this. I can rewrite this as 1 plus 0.5 x, right? Did I rock anyone's world? Okay. I can rewrite 1.5 as 1 plus 0.5 because I wanted to get it to look like this, right? So that's why I rewrote it. That's why I chose to rewrote this. What would my R be in this case?
0.5.
Yeah, R equals 0.5. Now, generally, a lot of times we want to convert this to percentage. That's what we like to do a lot of times. So how would I convert this 0.5 to a percent? Someone on this side of the room.
Calculator. Move the decimal.
How many? Where? Which way?
To the right.
How many?
Once.
How many?
Once.
How many?
One time.
Twice. Twice. 1, 2. So that would just be 50%, right? Any questions on this one? Okay. Now moving on to this one. Y equals 0.8 raised to the x power. Is that exponential growth or decay? Why?
It's not greater than 1.
Yeah, so it's less than 1. Yep. So this would be decay. Because the 0.8 is less than 1. Now, I can rewrite this, can't I? How would I rewrite this?
1 minus
How would I make it 0.8?
1 minus 0.2.
Yeah. The reason why we converted it to like this is because we're following the exponential decay model formula. That's what we're doing. Okay? That's why we converted it that way. Because it's really convenient to tell you the growth or decay factor going this route. Okay? So in this case, what might R be?
0.2.
From this side of the room, how do I convert it to a percentage?
Move it to the right twice.
Right. So what would be my percentage be?
20.
Yeah, 20%. Feeling good about that one? Okay. Now this one, is this growth or decay?
That is
This side of the room, growth or decay?
decay.
Decay, why?
Because it's not one.
It's
Not a whole.
Is it less than 1 or greater than 1?
Less than one.
Less than 1. So that's how we know it's decay. Okay. I can rewrite this. I can kind of rewrite this a couple different ways. The way my gut tells me I want to rewrite this is 1 minus, and then how many would I have to take away from 1 to get me to 2/3?
1/3.
1/3, right. I can rewrite this 1 as 3/3, and it be the same thing to get me to 2/3. Does anyone have a preference which way I write it? 1/1 or 3/3, they're the same thing. My preference is 1/1, and that's going to get me to 2/3. Okay? So what would my decay factor be in this case? Yeah, equals 3, or 1/3. 1/3. How would I what's that as a decimal? 0.3, 33.3% repeating, with the 3 going on till the end of time. Okay, sometimes you're asked to graph these. Do you guys have a preference which one I graph?
How about we graph the first one?
Do we feel good about that? The first one? Do we want to graph that one?
Yeah.
Okay, we can graph that one. Okay. So I'm going to graph the first one. So y equals 1.5x raised to the x power. And then I'm going to make myself an x and y table. Numbers I want to pick generally are like -1, 0, and then 1. I'm running out of room. So I can kind of plug this into my calculator on 1.5. And then how we do this is we raise it or hit the caret key. One of the two, the up key, caret key, same thing. And then we can kind of type in our numbers. So -1, that gives me like 1/3 or 2/3. And then I want to type in 0. That gives me 1. When I type in 1, what should I get?
1.5.
Yeah, 1.5. So now I can kind of plot these points. I can keep picking points if I wanted to. I could pick -2, I could pick -3, I could pick 100, I could pick -1,000,000 if I wanted to. I just typically try to choose 1, 0, and -3. Those are the ones I like to pick because they're easy. I'm all about making it easier than it needs to easier, okay? What?
What were the 3 points that you said you picked?
I normally pick 0, -1, 0, and 1.
Okay, I thought you said 0.
Oh no. Nope. So at 0, I'm going to be at 1. At -1, I'm going to be at 2/3. And then at 1, I'm going to be at 1.5. So my points all kind of are pretty close together. But I know the graph is going to look something like this, right? Because that's what they always look like. Something like this. It'll either look like this or it'll be switched the other way. One of the two. Okay? Identifying growth or decay and which way it goes is always very helpful. Okay? Any questions on that? Where would my y asymptote be? Or my asymptote be? Where would it be? Jackson, where would my asymptote be?
I don't know.
In this case, would it be y equals 0? Did it go up or down anywhere? No. So our asymptote is always at y equals 0. So it's going to be right along here. It's never going to touch the line, okay? But is it going to get really close?
Yes.
Yes. It's going to get so close, you're going to be like, it's like a sibling or a cousin or whoever is like got really close to you and it's like, I'm not touching you, I'm not touching you, I'm not touching you. It will never touch you, okay? Although sometimes they do. Okay, so real life application of this. We get to compound interest. We get compound interest deals a lot with banking. It deals a lot with loans, mortgages, car insurance, student loans, These are all compound interest type things. Every once in a while you get continuous interest, which we'll talk about in a minute. But basically what all these things are, P is your principal, not Mr. Todd. Principal, think like your initial. Principal. Something like that, principal. Okay? I misspelled that, I know I did. That's your principal. That's your starting amount. Your initial amount, that also works. But P, like your starting amount. R typically refers to a rate. N typically refers to our compounded number. I misread that. Number of compounds per year. A lot of times in story problems, they'll give you this as, I'll straighten that out, number of compounds per year. A lot of times in story problems, they'll give you this as like, this was compounded annually. So how many times a year would this be compounded? Once. This is compounded quarterly. How many times would it be compounded?
4.
Yeah, 4 times. This is compounded monthly. How many times would it be compounded? 12. This is compounded biannually. How many times would this be compounded? Twice. Biannually.
Yeah.
Twice. 2 times in the year. 2 times in the year. So you just kind of have to look for stuff like that. Okay? That's our overall goal. Okay? And then T stands for number of years. So time. Or number of years. And then A just is like in the account after 2 years. Like that's what A is up there. I think of it as the end amount. That's what I think of it as. Because this formula also works for loans and stuff like that. It's just not the number at the end of it. It's not just an account that you'd use this for. You'd also use this for loans as well. Okay? So an example. You deposit $9,000 in an account that pays 1.46% annual interest. Find the balance after 3 years when the interest is compounded quarterly. Okay? So they threw a lot at you, and we have a lot of different variables we're working with. I typically like to write out my variables and see what I get. Okay, do I know A? No, so that's my question mark. Do I know my principal? How much am I starting off with?
9,000.
What was that?
9,000.
9,000, right. 9,000. What's my rate?
1.46.
Yeah, 1.46%. Drayden, what's my time? How long is this going on for?
I don't know.
Well, let's read the story problem. How many years? 3 years. You're right. 3 years. Okay. So now we kind of know. Now we kind of know what we're working with. Okay. So now we can kind of plug it into our formula. Okay. So P would just be 9,000. Okay. 1 plus. The rate over N. Oh wait, no, I forgot N. You guys let me forget N. How many times does this get compounded a year if it's compounded quarterly? 4 times. Yep, N is 4. So it'll be rate over N. Now, when I have rates in terms of percentage, I need to convert this to a decimal. Can anyone tell me how to convert a percentage to a decimal? 2 to the left. Remember my girl Beyonce. To the left, to the left. That was funny. The last class laughed at my joke. Come on, guys. I'm here all day. So if we move this 2 to the left, that's going to be 0.0146 divided by N was 4. raised to, so up here we have an n and we have a t, so that's just going to be 4 times 3. Okay. Now we can kind of plug this into our calculator. It's not going to look pretty. I'm not going to lie. Okay. But we can do it. So that's 9,000 times 1 plus 0.0146 divided by 4, close your parenthesis, caret key, you need another parenthesis, 4 times 3, okay? And that's going to give us our answer. It's not looking pretty, but it's going to give us our answer, okay? Equals 9,402.21. What's my unit on this? We're talking in terms of money, so dollars, right? Never leave naked numbers. They don't appreciate it. Okay? Yeah. Okay. Any questions on this? Oh, can you wait like a couple minutes? We're going to talk about like a very interesting thing. Okay. All right. Any questions before I move on to the next thing? Okay. All right. Oh, yep, I can go back. Yep. My bad.
So did we find out what A was?
Yes, this would be A.
That's A, okay.
Yes, this is A. Yep.
Thank you.
Yep. Okay, we're good? Anyone else? Wait, or am I good to go on the next page? Good to go? Okay. All right, next page. We're going to learn about something new today, where I'm giving you a new number to think about. Okay? It's called E, the natural base E. It's an irrational number. It's a lot like pi, but we generally use this when we're talking about like continual growth. We talk about this like continual interest. We talk a lot about this. We also talk about this in terms of population growth. A lot of times we'll use this formula. But really what it is, it's just continual growth. That's a lot of times what we use this for. Okay? It can be approximated by, as x approaches infinity, by this amount here. So let's type it into our, I'll show it to you. I'll prove it to you. Someone name a big number. 2,000? 5,673. I'm going to go with that one. That's kind of a cool number. Okay? And I should get like this 2.71. I should get that. Okay? Let's see if I get it. So I get 1 plus 1 divided by, what was it? 5,763?
I don't even
65? Okay.
It was like 69, I think.
Okay, let's leave it at 65 for right now, because that's what I think it was. So 5,765. Whoa, I typed something in wrong. Oh, I did. I need an extra parenthesis. .71. I got pretty close, didn't I?
Yeah.
Yeah. 2.718. I got doggone close. Typically, you know how pi we use 3.14? For E, typically a lot of times we use 2.72. It's just what we use. It's a convention of math. That's what we use. This E, it's an irrational number. It's going to keep going on forever and ever and ever and ever. It's never going to stop. Till the end of time, it'll go on. Okay? It's a lot like pi. It operates the same way. Okay? So there's, that's E. So sometimes we use E in functions. We'll use that in functions as well. So the general function for a natural base exponential function, when I say natural base exponential function, that's just a fancy term for it has E in the function somewhere. That's what it is. The general function is just going to be y equals a times e to the rx. That's what it's going to be. Okay. A, again, is going to work a lot like a vertical stretch or shrink. Okay. When a is greater than 0 and r is greater than 0, this is typically referred to exponential growth. when a is greater than 0 and r is less than 0, this is referred to as exponential decay. Okay? So here, the important thing to look at is the r, where on our just a normal exponential function, the important thing to think about was the b. That's the difference between the two. Okay? So moving on. So some examples. 3 times e to the x. Is this exponential growth or decay?
Growth.
Growth. Why?
Because both A and R are greater than 0.
Yep. So that would be growth. Someone else. For our next one. Is this growth or decay? Decay. Why?
Because it's less than 1.
Yeah. This negative 0.5 is less than 1.
Less than 0.
What? Oh, yeah, less than 0. My bad. Thanks for catching me. Less than 0. Okay, you might be asked to graph these too. Do we have a preference on which one we graph?
Let's do the one that's the growth one.
The growth one? We did growth on the last one. Can I do decay here?
Okay.
Yeah, will we all be good? Okay. All right. I want to choose this one for my graphing it. So I'm going to choose an XY table. Okay. I like to pick -1, 0, and 1. Those are the ones I'm partial to. Now, does anyone know where the E key is on your calculator? Anyone?
It's on the ln.
Yeah, right above the ln. ln stands for natural log. We'll talk about it in a little bit. But that's what it stands for. Why it's ln and not nl, I have no idea. I'm going to look that one up today. But, yeah, I'm going to look it up. That was pointed out last hour. I was like, what? I've never thought of that before. Okay, so it's just right there. So here we have second E, second ln, that's what it gets you. And then I have like this negative 0.5, and let's say times -1. That's going to give me like 1.64, right? Now I'm going to pick 0. What should it get me? Any ideas? 1. Why?
Because anything to the power of 0.
It's always 1. Right. Now the next number I want to pick is positive 1. Kaylin, do you think I'm going to get a number that ends or a number that doesn't end? Do you think I'm going to get a big long decimal, or do you think I'm going to get something that's like really short and sweet? What? Short and short? Let's see what happens.
No.
Ooh, I got a big long decimal. Okay, so that's the 6.1. Okay, so this is going to look something like this when I put it on the graph. Which one should it look like before we even go any further? Should it look like this one, or should it look like this one? Who thinks the first one? Who thinks the second one? Yeah, it's decay. Yeah, good job. So it's going to kind of look like that. So it looks like that. Then we have 1, and then we have 1.16. And it's going to kind of look like this. This is what the function is going to look like. Where's my asymptote at? Hmm? What? Yeah, it's at y equals 0, isn't it? So my range would just be, what would my range be? Yeah, all y greater than 0? Yeah, because the negative ones don't work down here, do they? Will it ever take on a negative value? No. No, it'll never take on a negative value. Okay. What would my domain be?
All real numbers.
Yeah, all real numbers for my domain. Okay. All right. So last thing, and I promise I'll be done talking at you, and then we can work on our homework assignment. Okay? So we have one more formula to talk about, and it's continuously compounded interest. Sometimes you do this with banks, sometimes you don't. This is much more rare to see in the world of like business and finance, just because things grow a whole lot faster here. And bank people generally don't want to pay more money than they have to, in my experience. So a lot of times they just choose compounded interest over continuously compounded interest. It also is used a lot in population growth formulas. This same formula gets used. Okay. I generally like to think of it as the PERT formula. Okay. To see how it's written, P-E-R-T, PERT. That's how I remember it, PERT. P is principal, so like the amount you're starting with. E, that's just this number from up here. That's all it is. 2.72, that's what it is. R is a rate. And then T is in time. Generally years. Okay. That's our PERT formula. Okay? So now we get down to our example. So you deposit $4,250 in an account that earns 5% annual interest compounded continuously. That's our clue for the PERT formula. What is the balance in the account after 10 years? Okay. So I'm going to list out variables because I think that's incredibly useful. A, again, here is like count at the end. Do I know A? No. Question mark. Do I know T? What is it? 10 years. Right? Rate. What's my rate? 5%. What's my principal? 4,250. Right? Do we see that? Now I can plug it into my formula. So I have 4,250 E. Now I have a rate. Who do I remember? Yeah, I got to move it to the left. Got to remember Beyonce. To the left, to the left. 2 places to the left. So that would just be 0.05. And then we have time, which is. We can just plug this into our formula. Or plug this into our calculator because we know that. So we go over to ln 0.5 times 10. And it's going to give us $7,007 and $7 and 7. Yep. What's the unit on this? Dollars. Never leave naked numbers. They don't appreciate it. Okay. Are there any questions on this? Kind of what to look at? We all kind of have a good grasp on this. Okay. Need to. The recording of this lesson will be posted online relatively soon, so you can go back and look over it. If you don't have any other questions, you do have a Big Ideas math assignment that we can get working on. Just go to Canvas, and it's going to be right there. And I can't think of any other way to end the day than doing math problems. So let's rock and roll. Talk too long. Yep, there's my sign. Talk too much today.
Okay, let's see. So then I'll just hit this.